advantages of fixed beam over simply supported beams for same span and loading condition, then followed by the disadvantages. And then we learnt about the continuous beams, their advantages and disadvantages. Okay, right. So now we will learn about the analysis of, we will learn about the analysis of the fixed beams. Right. Okay. So before I go to the analysis of fixed beams, or let us take the heading. Let us take the heading as fixed beams. Okay. So let us say we have the fixed beam like this. Okay. Yeah. So we have a fixed beam. This one, this end is fixed. This is A and this is B. Okay. And we have two loads over here. This is, let's say, W1 and this is, say, W2. Right. Okay. So now let us talk about the reactions over here. Okay. So here we'll definitely have a reaction. Let us say we represent it as or RFA. Let us represent this reaction as RFA, that is a reaction for fixed beam at support A, and here we have the reaction for fixed beam at support B. Okay, now let us say we have the moment generated at A in the anti-clockwise direction. Let us say I'm taking the center as A. So the moment generated is at A due to the fixed end is MA, and at B, let us say we have the moment as MB, right? And let us say the span of this beam. I hope everything, whatever I'm writing, it is clear to you. Can we see it properly? Please respond.
So,
Okay. So let's write some details about this drawing. Okay, whatever we have drawn. Okay. So let us say a fixed beam. See, whatever I'm writing, you can write it. You can take down these as notes. Okay. So let us say a fixed beam AB is subjected to loads W1 and W2. I have not mentioned what is the distance between these two loads and all. For the time being, I have not mentioned. Okay. Now, another point is, let RFA and RFB are the reactions of this fixed beam AB. Okay, let us say RA and RFA and RFB are the reactions at the supports. Let us write at the supports A and B respectively of this fixed beams. Okay. Now let us say MA and MB. Okay, this one, MA and MB. These are, let us say, see, these moments have developed due to at the fixed ends. Okay, so we can call them as fixed end moments. Okay, so MA and MB are the fixed end moments, right? Okay, now, so the analysis, see, So here, see, in the question, whenever a question is given or whenever a problem is given, so at that time generally this w1 w2 will be given. Okay, and what is the distance between all these things will be given. Now what are the unknowns? The unknowns in this question, okay, generally the unknowns in this question will be this one: RFA, RFB, MA, and MB. Okay, so and we know that we have two equations of equilibrium for this one. Okay, so that is summation Fy equals to 0, that is 1, and summation of moments at a point is 0. Okay, so we have two equilibrium equations and we have four unknowns. Okay, so we fall short of, so four unknowns minus two equations of equilibrium means 2. So we need another additional two conditions in order to find out the moments. Okay, so that can be done in two stages. Okay, so here we can write the the analysis of this fixed beam can be done can be done in the following two stages. Okay, now what is the first stage? Okay, so let me change the color of the ink so that it will look somewhat good to you. Okay, so the first one, let us say it is stage 1. Let us say we are talking about the stage 1. Now what is the stage 1? So let me draw the fixed beam again here. Okay, so this fixed beam having the loads, this is W1, this is W2 again, this is A, this is B. Okay, and the overall length of this beam is, let's say, L. Okay, so this can be considered as a combination of a simply supported beam. Okay, okay, so here again I can put these two loads here. Okay, let us say this one, here I'm having W1 and here I'm having W2. This is A, this is B. Okay, let us say the reaction here is RA and the reaction here is RB. Okay, right, and let me take a cross section here. For example, I'm taking, okay, let us say I'm taking a section over here. Okay, this is X. Okay, so this one, so if, so this is stage 1. Okay, I'm talking about, this is stage 1. Okay, so it will be consist of a simply supported beam and with having these two reactions RA, RB. Okay, so now if I draw the free bending moment diagram, if I draw the free bending moment diagram for this one, then it will be, so this one, so let us say that W, okay, or I'm drawing the arbitrary bending moment diagram, free bending moment diagram. This is, okay, let us say it is here. Okay, right. So the bending moment diagram for this one will be somewhat here, and let us say the section X is going like this. Okay, so this one we are considering it as mx. Okay, mx stands for, or mx is the moment of, or the free bending moment diagram. Okay, free bending moment diagram. Okay, so this one, so the section here, this section X is at a distance of x bar, or the CG. The CG of this one, it is, sorry, not here. The CG is at a section, or it is at a distance of x bar. The CG of this whole bending moment diagram, it is at a distance of x bar from the end A. Okay, this is end A, this is end B. Okay, so here we can write, so we can write like this. So the explanation part for this stage 1, it is the beam is treated as a simply supported beam carrying point loads W1 and W2. Okay, now let RA and RB be the reactions at the supports A and B respectively. Okay, so here see, here this RA is the uh, reaction at support A, and RB is the reaction at support B. Okay, now this is stage 1, and the next stage is stage 2. Now what is stage 2? Now what is stage 2? Okay, so the stage 2 is again similar. So it is a simply supported beam again. Sorry, yeah, this is again a simply supported beam, and here we are considering that here we have the moments MA and MB okay. So we have the moments MA and MB, where so we can write this one, where, so if I draw, so here we will not be considering any externally applied loads, only the moments will be there. Okay, so whatever moments which we say that it will be developed here, MA and MB, so those fixed end moments will be here. Okay, so now for that, the fixed end moment diagram will be similar one, right? Will be similar one. So this is MA, this is MB. Okay, so here it is MA, here it is.
Sir, excuse me, sir.
Just a moment. And the CG of this one is at a distance of x bar dash, and this is the fixed bending moment diagram. Yeah, someone was asking some doubts, please.
Sir, first free bending moment diagram you have drawn, no, sir.
Yes.
That slope starts to change A to W1, no, sir. You starts to change that XX
Okay. Yeah. Yeah.
plane,
Yeah.
sir.
Yeah. 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 Sorry. Yes. Yes. It is from here. Okay.
Yes, sir.
Now it is correct.
Yes, sir.
Yeah. Okay. Thank you for that. Okay. So any other doubts you have now? No. Okay. So so now what is the explanation for this stage 2? So now we can write that in the stage 2, in the stage 2, the simply supported beam is considered under the action of MA and MB, that is the fixed end moments without the given loading. Right? Okay. Now, apart from that, since these are the supports, so here we will have one reaction, which let us say, so here definitely there will be reactions due to these movements. So let us say that reaction is R, it is in this direction, and another reaction is in this direction. We are assuming it. Okay. So we are saying that let R is the reaction at end under the condition, under the condition that is MB is greater than MA. Okay. So if this is the case, and see one more thing, what is the distance between this A and B? The distance between the supports, it is small l. Okay, or l, whatever it may be. Okay, now what will be this reaction R? So if MB is greater than MA, can I write R equals to MB minus MA by L? Can I write like this? The reaction R will be given as MB minus MA by L. Okay, now you may say, sir, from where this one came? Okay, so here we have two fixed end moments. Okay, so if I take moment at this point, so it will be R into L. Okay, R into L equals to, I'm considering MB is greater than MA. So it is, I'm taking moment about this point. So R into this L. Okay, so it will be a clockwise one equals to MB minus MA. So this implies R equals to MB minus MA by L. Okay, so from this we got this value, the same. Okay, so now if I combine stage 1 and stage 2, okay, so if, so let me write this. So combining stage 1 and stage 2, what we have. So if we combine stage 1 and stage 2, okay, this one and the other, okay, so let me draw those once again here for your clarity. Okay, so what we are saying, so here we have this one, okay, and here I have, this is W1, this is W2, this is A, this is B, and this is this I told RA, this is RB, right? And the free bending moment diagram was, let us say, okay, and for example, let's say this is the CG of the free bending moment diagram. This is at X bar distance from the support A, and this is mx, okay, it is, or I can write it as m subscript, not m into x, it is m subscript x, okay. Now, and we are having another one, okay, so, and this is a section x, okay, so another one is again a simply supported one, and here I am having the fixed end moments MA, MB, okay, and here the fixed end, so this is free bending moment diagram, okay, and this is fixed bending moment diagram. So fixed bending moment diagram is, let us say this will be MA and this is MB, okay, so this is MA, this is MB, okay. Now if I combine these two bending moment diagrams, if I combine this one and this one, then what will be my resultant? What will be my resultant? So my resultant will look like somewhat like this. So this one is the B. Okay. So the first one, let us say I have drawn. I'm drawing it roughly. Okay. And so this loading, it comes here, and we have another loading. This is coming here, so I can write, or let me change the ink, or let me take the red color, right? So this will be the, this we call it as the resultant bending moment. This is the resultant bending moment diagram. Okay, now, so this one, so here it will be, I'll just make something here. So it will be, this part will be having negative, this will be positive, and this will be negative one. Okay, now what are those values? What is the yeah, what are those values? So this you already know, this is MA, this is MB. Okay. Now, how to find the final bending moment diagram? Okay. Now, what about, okay, so here we had RA and RB. Okay. And here we have RFA and RFB. Okay, sorry, not that one. That one is the, so before that we are having, so here we have RFA and this is RFB. Okay, so this we are taught, we have divided it into two parts. So can I say that RFA and RFB? So can I write, the final reactions? Okay, the final reactions are given as, the final reactions are, can I write RFA equals to RA minus R and RFB equals to RB plus R. Now see, so here we had, this is R and here the direction of R was this. Okay, so that's why, so RA minus R and RB plus R. Okay, now if I take any section on this free bending moment diagram and this bending moment diagram, okay, can I have this equation? So the actual, so you can write the actual bending moment at any section x at a distance of x from the support A. Okay, now I am saying that this is at a distance x and this is the CG. Okay, this is the CG of this one, and here, for example, let us say this is the CG. So this is the CG of this fixed bending moment diagram is at a distance of x bar dash. Okay, so the actual bending moment at any section x at a distance of x from the support A is given by, we have EI into d square y by dx square equals to mx, it is m subscript x minus mx again mx dash. Now what is this mx? So mx is this one, that is the free bending moment diagram, and mx bar is the fixed and bending moment diagram. Okay, so this becomes the equation 1. Okay, this is equation 1. Okay, now in order to, okay, now you may ask, sir, what is this y? Y is the deflection at the, or deflection of this beam, or deflection of this fixed beam. Okay, so here see, so when the beam will deflect, it will deflect somewhat wait, it will not, yes, so it will deflect somewhat like this. Okay, so here at this end the slope will be 0, and here the slope will be 0, and here we will have some value of y. Okay, so that y we will get by or from the integration of this equation 1. Okay, now if I integrate both the sides, okay, if I integrate both the sides, then what I will have. Okay, so integrating both the sides, so it is, so if I integrate this one, so again it will be ei into dy by dx. Okay, and it will be from 0 to L. Okay, equals to integration 0 to L mx dx minus integration 0 to L mx bar dx. Okay, now what is dy by dx? What is this dy by dx? So dy by dx is the slope here, slope. Okay, dy by dx at slope. So at if at x equals to 0, okay, so we are finding out the uh, moment here, or okay, x. So when this x is 0, the slope will be 0 here. Okay, so I can write at x equals to 0, at x equals to 0, we have dy by dx equals to 0, right? Now at x equals to, when we consider x equals to L at this point also the dy by dx value, that is the slope, here it is 0. Okay, so I can put a comma here. At x equals to L, sorry, at x equals to L, at this point, okay, at this point also the slope is 0, so that is at x equals to L, dy by dx equals to 0 again, right? So we have these both these two conditions. Okay, and what is this integration of 0 to L mx dx and integration of 0 to L mx bar dx? So that is the area of, so the first one is the area of the free bending moment diagram, and second one is the area of the fixed bending moment diagram. Okay, the area of this one. Okay, so we can write like, so also integration of 0 to L mx dx equals to area of the free bending moment diagram and let us say the area of this free bending moment diagram, we are representing it with A. Okay, okay, and this integration 0 to L mx bar dx, this is area of the fixed bending moment diagram, and let us represent it as A dash. Okay, now if we substitute this value, and these two conditions, then I can write, okay, so dy by dx at 0 to L. Okay, so these two values, it is 0. Okay, all this dy by dx is 0. So I can write, so substituting these two conditions in equation 1. In equation 1, can I write ei into 0 equals to a minus a dash. So anything multiplied by 0 becomes 0. This implies 0 equals to a minus a dash. So this implies a equals to a dash. Now, what does this mean? If a equals to a dash, it means that the area of the free bending moment diagram and the area of the fixed bending moment diagram are equal. Okay, so that inference we can write it here, that is area of free bending moment diagram is equal to the area of fixed bending moment. Fixed, what happened? Sorry guys, I think that got disconnected. What happened? Yeah, yeah, is equal to the fixed bending moment diagram. Okay, right. So that is the first inference we get again. And let us consider, or considering again, considering equation 1. Now what is equation 1? As I told earlier, see here, equation 1, this one. Okay, equation 1. So again, considering equation 1, that is d square y by dx square equals to mx minus mx bar. If I again consider this one, and if I multiply x on both the sides, so multiplying x on both the sides, okay, multiplying x on both the sides. So if I multiply x on both the sides, so ei into x into d square y by dx square equals to mx into x minus mx bar into x. Okay, now again here, if we integrate, okay, so integrating both the sides, we have, okay, now if I integrate this one, so it is integration 0 to L, it is ei into x into d square y by dx square equals to integration 0 to L mx into x into dx. minus integration 0 to L m x bar into x into dx. Okay, so now if I integrate this, so here we have the x and here we have this one, so this I can write it as, so ei into x into dy by dx minus y equals to 0 to L equals to, this one equals to ax bar minus ax bar dash. Okay, now where this x bar, where this x bar, what is this x bar? So x bar equals to distance of the centroid of the free bending moment diagram, and x bar dash is the distance of the centroid of the fixed bending moment diagram. Okay, so as I said earlier, so now what we will do, we will put the boundary condition. Okay, the boundary condition is, so as I told earlier that at x equals to 0 and at x equals to 0 the and y equals to 0, we have dy by dx equals to 0. Okay, and at x equals to L and y equals to 0. Okay, these two points. Okay, at x equals to 0 and y equals to 0 and x equals to L, y equals to 0 here. Okay, so here there is no deflection. Okay, so x equals to 0, y equals to 0. Again here also dy by dx is 0. Okay, so this is, okay. Before that, let us or number the equations so that it will be easier for us. Okay, now let us say this is equation 2, and here we have found out a dash equals to a. This is equation 3, and this one is equation 4. Okay, so if we substitute the value of equation 4 in or wait, this is, let's say this is equation 4, this is equation 5. So substituting equation 5 in 4, we have so it is ei into, this is 0 minus y is also 0. Okay, equals to a x bar minus a bar x dash bar. Okay, so this implies ax bar equals to A bar X bar dash. And we already know that A equals to A bar. Okay, so if A equals to A bar, then this gets cancelled out. So this implies X bar equals to X bar dash. So that is the centroid of of the free bending moment diagram, and the fixed bending moment diagram will be 1. Okay, so this is the completion of this one. In the next class, we will learn about the different special cases. Okay,